In this illustration, we are going to study about the electric potential at the edge of a disk. Here, we are required to calculate the electric potential due to a uniformly charged and non-conducting circular disk at a point lying at the edge of a disk. And we are also given that the surface charge density on disk is sigma coulomb per meter square. Here, if we draw the picture, say if this is the circular disk, on surface it is completely charged at sigma coulomb per meter square. And we are required to find the electric potential at this point A. Then here what we can do is, there are several ways to evaluate it. Here what we can do is, in one method we can consider an elemental section at an angle theta which is of angular width d theta. Now on this rod, if we wish to find out the electric potential at one end, then again we need to go for an integration. Then at a distance x from point A, we consider a small elemental section of width dx. Due to this element, potential at A can be written as k dq by x. But for this, we first need to calculate the charge on elemental section is, here this can be written as dq, which is sigma multiplied by the area of the section, which is its width is dx and the length on the other side is x d theta, because this angle is d theta. So this can be written as dx multiplied by x d theta. Now due to this dq, if we calculate the potential at A due to dq is dV, and this dV can be given as k dq by x. If we substitute the value of dq here, one x gets cancelled out and this will give you k sigma dx d theta, because here I am taking this x get cancelled out in numerator and denominator. Now we need to integrate this potential twice. One is for the variable x, keeping theta as constant, and then we need to integrate it for the value of theta from minus pi by 2 to plus pi by 2 for the whole disk. So in this situation we can write total potential at A is, this v can be given as integration within limits of theta from minus pi by 2 to plus pi by 2, and then we'll further integrate it for the value of x. If we take this the center of a disk and r is the radius of this, then this angle will also be theta, because this elemental strip is acting as a chord of the circle. So here the length of this chord will be 2r cos theta. So x will be integrated from 0 to 2r cos theta. So this is k sigma d theta multiplied by dx. So when we are integrating for the value of x, the value of theta d theta remain constant. So this term we take out of this sign of integration. So this potential will be integration from minus pi by 2 to plus pi by 2. K sigma d theta will be a constant, and x will be integrated within limits from 0 to 2r cos theta. So this dx will be integrated as x. We apply limits from 0 to 2r cos theta. So this will be integration from minus pi by 2 to plus pi by 2. This will be 2r k sigma cos theta d theta, which can be further written as this 2r k sigma. Here we can substitute the value of k. So this will be sigma r by 2 pi epsilon naught, and we integrate cos theta, which will be sin theta, and we apply limits from minus pi by 2 to plus pi by 2. This will give us sigma r by 2 pi epsilon naught, and on substituting the limit pi by 2, this 1 minus of sin minus pi by 2 is another minus 1. So this will be 2. This 2 gets cancelled out with this, and the result is sigma r by pi epsilon naught. That is the answer to this problem.